Cuéntanos.
I'm David Suzuki. Whales are majestic, mysterious animals that have long intrigued us because they're so obviously intelligent. They use sound to communicate and navigate over immense distances. But now a radically new proposal has been put forth. Do whales focus powerful sound waves to stun their prey? A few years ago, a diver in California was swimming in a tank closely followed by a beluga whale, like these ones here. Suddenly, he heard a loud bang and felt a shock wave pass through his body. He scrambled out of the pool, looking about for an explanation, possibly an explosion, but no one had heard a thing. His conclusion was that he had been zapped by a beluga. We hardly know anything about the complexity of life in the ocean. And sound must be used in ways that we can't even begin to imagine. The ocean is filled with strange and wonderful noises. It's an acoustical world, where many creatures depend more on their hearing than they do on their eyesight. That's because underwater, sound travels much farther than light. The best-known sound from the sea is the song of the humpback whale. It's even been featured on a popular recording. No one knows why the humpback sings, but it's unlikely that these sounds are used to stun prey. Humpbacks are baleen whales, and they have no need for stunning sound because they feed on tiny organisms that are free-floating or swim too slowly to have any chance of escape. The toothed whales are the cousins of the baleen whales. There are 68 different species, ranging in size from the tiniest dolphin to the mighty sperm whale. They are predators, and they all use sound to hunt their prey. Many of the creatures they feed on are fast and elusive, and could be more easily caught if they were debilitated by sound.
There's no doubt about it. The killer whale is a toothed whale, as you can see from this animal at the Vancouver Aquarium. With 52 impressive teeth, killer whales are highly efficient predators of everything from herring to giant blue whales. But nearly half of all toothed whales have very few teeth, or teeth that don't function at all because they're misshapen or embedded in the gums. In some cases, it's hard to see how they can capture the prey species they depend on for survival. Take the narwhal, for example.
The cumbersome tusk of the male narwhal must severely restrict the animal's ability to turn quickly. Yet somehow, the narwhal captures shrimps that can swim very fast in short, evasive bursts. Could narwhals be using sound to stun their prey? Scientists have asked the same question about the sperm whale. But the sperm whale is almost impossible to observe because it feeds as much as 3 kilometers beneath the surface and stays submerged for an hour or more. These are squid, the favorite prey of the sperm whale. There are many species, some smaller than a human hand, and others, monsters, more than 10 meters long. It's hard to understand how the sperm whale can catch them, because squid have been clocked at speeds of 50 kilometers an hour, far beyond the whale's top speed. But catch them they do, even the giant squids, whose fearsome suckers are armed with sharp claws that leave deep scars in the sperm whale's head. To the hand whalers, the sperm whale was the mythic Leviathan. This was Moby Dick, prized for its oil and dreaded for its fearless attacks on the boats. Stranger than any mythology was the discovery by modern whalers that squid can be found in the sperm whale's stomach alive and without any apparent injury. How then do sperm whales capture their prey? Some scientists suggested they must stun their prey with sound.
It was an interesting hypothesis, but it couldn't be tested because no sperm whale had ever been held in captivity. They feed at sea at such a depth that they couldn't be observed. So scientists began to study dolphins to test the hypothesis. We've known for years that dolphins have a highly developed sound capacity for echolocation and communication. But can they stun their prey?
Scientists first had to determine whether dolphins could make sounds loud enough to stun. But dolphins don't emit their loudest sounds in tanks because they are bothered by echoes bouncing off the tank walls. Dolphins are known to make much louder noises in the wild, but their vocalizations can't be measured accurately under conditions at sea.
To get a true reading, scientists in Hawaii placed a dolphin in a cage in the ocean and then trained it to echolocate a 7-centimeter steel ball like this one. Then they moved the ball farther and farther away, forcing the dolphin to make louder and louder sounds to echolocate it. Finally, when the ball was over 100 meters away, the dolphin was putting out sounds more than 5 times louder than its vocalizations in a pool. That's powerful enough to stun or even kill a fish. But that observation doesn't prove that the dolphin actually uses those sounds on its prey.
The search for proof continued in Hawaii and Florida in the early 1980s. Scientists put fish into a tank with dolphins and watched as the dolphins bombarded the school with high-frequency sound. The sound clearly had an effect, but it was not what the scientists expected. Professor Ken Norris, a marine mammal specialist at the University of California, conducted the experiments in Hawaii.
What we were looking for, of course, was the big bang. We hoped that the dolphin would simply go in and go bang and the fish would turn over and that we would have our proof. And in fact, what happened was that the dolphins went in over a matter of half an hour or so, and it was only after that length of time that we began to see an effect. And we finally saw fishes that couldn't find their school, ones that seemed disoriented, and one actually got sucked down the drain. We were left with a puzzle. What had happened to the fish wasn't absolutely clear. We thought that it was the sound that had disoriented them, but we weren't sure. And so the search went on. We thought we had evidence, but we weren't sure.
Meantime, acoustic specialist Dr. Ken Martin was pursuing another line of research in Hawaii. He spent months training a dolphin to put out extremely loud sounds on command. Then he gave it a living target.
He put a fish in a plastic bag and lowered it into the water. The dolphin hit the fish with powerful bursts of sound, but much to Martin's surprise, there was no apparent effect on the fish. For the moment, the research had come to a dead end. A breakthrough came here, just off the San Diego waterfront. Ginny Cass, a graduate student in biology, was recording the sounds of Pacific bottlenose dolphins with an underwater microphone. The dolphins were putting out their normal high-pitched echolocation signals. But then they came across a school of fish, and when they began to feed, some very different sounds came through Ginny Cass's earphones.
Are so different than any of the other sounds you usually hear from these dolphins. Usually you hear echolocation clicks and whistles. These sounded more like a machine gun going off or rifles going off, one right after the other, with a bang, pop, and some boings and gulping sound.
Blah, 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 blah machine gun sound that you just heard from Ginny Cass's tape introduced a whole new set of information for us from the wild in this case. In particular, once we analyzed the sounds, we found that each bang is a very long duration, probably 100 or even 1,000 times longer than an echolocation click. And when we analyzed the energy distribution of a single bang, we find that it is not the high-pitched type of sound that I was looking for in Hawaii, the type that's outside of our hearing range, but it's in fact very low-pitched. We can hear it very well. And it's down in the hearing range of fish, right in the optimal hearing range of fish. And this leads us to the hypothesis that the mechanism of disorientation or stunning is not just some kind of bodily injury to the fish's swim bladder or body organs, but is rather an assault on its hearing apparatus and temporarily disorients the fish and makes it easier to capture.
In 1983, Ken Norris and a Danish colleague, Bertil Moll, published a paper on the stunning sounds hypothesis. The article was controversial, and some scientists say premature. Norris knew he was sticking his neck out.
Well, we decided to publish the paper after we had developed a series of suggestive lines of inquiry, that all of which led to the conclusion that it seemed likely that dolphins caught their prey by sound, and yet we weren't able to prove it. And we couldn't see how we could develop that proof easily ourselves. And we hoped that by getting people's minds turned this way, that people would begin to observe more widely and that we might come up with it.
A year later, just such an observation was recorded on this home movie film at a place called Monkey Maya on the west coast of Australia, where wild dolphins have become tame. Two American students, Rachel Smolker and Christine Johnson, were studying the dolphins when they witnessed what they believed was the use of stunning sounds.
The animals would be approaching the fish. You'd see sort of a bow wave. It was swimming really rapidly near the surface, and you'd hear the echolocation whine sort of, and then you'd hear this crack sound, and the water would sort of splash up, and the fish would come tumbling out, head over tail, and plop down and then be scooped up by the dolphin.
Christine Johnson attempted to film the dolphins feeding. Although unclear, her pictures do show fish coming out of the water after loud bangs were recorded.
We got kind of excited about that because we'd heard about this hypothesis of them possibly stunning fish, and that's sure what it looked like was happening. And over the course of the time we were there, we saw this kind of feeding behavior, I don't know, many times.
Skeptics say the dolphins were just slapping the fish out of the water with their tails, which dolphins commonly do. The students disagree. Certainly the film is inconclusive. It's kind of like looking at pictures of UFOs. But the fact is, despite years of study, we know very little about the sounds that toothed whales make. That's because they live in a world utterly unlike ours. Consider what happens when we get into the water. Have you ever noticed that you can't tell what direction sound comes from underwater? That's because our ears weren't designed to hear underwater. But actually, water is a much more efficient transmitter of sound than air. In the water, sound travels nearly 5 times faster than it does through the air. Underwater, we feel sound as much as hear it because the sound waves enter into the body rather than bouncing off. When a bat sends out its echolocation squeaks, which are too high for us to hear, most of the sound bounces off the insect and comes back to the bat because the density of the insect's body is very different from air. When a dolphin beams its echolocation sounds at a fish, most of the sound waves pass through the skin and flesh of the fish because they are similar in density to seawater. The sound waves bounce back to the dolphin from dense bone or from air in the fish's swim bladder, giving the dolphin an ultrasonic image of the fish, just like the ultrasonics used in modern medicine. The only difference is that while we have to transpose the sound waves into a picture, the dolphin can get a detailed image of the fish from sound alone. Another big difference between sound in air and water is sound pressure. That's the jar your body feels from a very loud noise. That pressure is transferred with more than 60 times as much force underwater. And that's what makes a stunning sound possible. The difference can be demonstrated by exploding a giant firecracker close to a bottle. In the air, the explosion has no effect on the bottle. But try the same thing underwater, and the result is quite different. We share a common ancestor with the whales in our very distant evolutionary past. They were land mammals. But unlike us, the whales went into the water about 70 million years ago. They left the visual world of air for an acoustical one in the water. So they had to develop elaborate new capacities for producing and receiving sounds. Killer whales and other toothed whales are thought to produce at least 3 completely different sounds at the same time. And they can shift their sounds through a range of high and low frequencies that is more than 10 times as broad as the entire spectrum of human hearing. Sounds like these are incomprehensible to our ears, but thanks to the sonograph, we can see the internal structure of these strange noises. Dr. Frank Aubrey is a bioacoustic specialist at Hubbs Marine Research Institute in San Diego.
And we know that sometimes the same killer whale and the same dolphin can make sounds that are increasing in frequency, decreasing in frequency, and clicks all at the same time. Concurrent sounds like this. Why they do it, we don't know. This sound, for example, right here, shows that a whale is making 2 sounds at the same time. Right here is one sound that the whale is making, and then the fine lines sloping down at a different angle are another sound. So that whale is making two different sounds at the same time.
We know that dolphins and many of the other toothed whales use two different kinds of sound for echolocation. They put out a broad cone of low-frequency sound to make a general scan of the water in front of them. Low-frequency sound has long waves that travel farthest, but give the dolphin a fuzzy picture. They also project a narrow beam of high-frequency sound to examine things in detail. High-frequency sound has short sound waves that can be narrowly focused. It gives the dolphin a sharp sound picture. Have you ever tried to talk underwater? If you have, you know that your mouth can fill with water and you very soon run out of air. Marine mammals that vocalize underwater have developed a system for recycling air. They can put out sound continuously while submerged without releasing any air. Sound is generated deep within the dolphin's head and conducted to the forehead and upper jaw through fatty tissues, whose unique biochemistry makes them highly efficient sound transmitters. The dolphin's hearing system has also become adapted to life underwater. Evolution has reduced its external ears to all but invisible holes that are believed to have little, if any, hearing function. In their place, sound is received by the dolphin through a pan of very thin bone in the lower jaw and conducted to the middle ear through acoustical tissues much like those in the forehead. The fatty tissue in the forehead is called the melon, and it acts as an acoustical lens to focus sound. The rate of sound transmission through the melon is graded from slowest at the center to fastest at the outer edges, causing the sound waves to bend. And to project a more intense beam of sound, the animal can lengthen the melon, causing greater bending of the waves and a narrower focus. Nearly all the toothed whales have a melon in some form. None displays it more dramatically than the beluga, whose forehead actually changes shape as the melon moves to focus sound waves. There is a theory for the evolution of acoustics in the toothed whales, and it goes like this. Sound was first used for communication, and then a sonar capacity was developed for echolocation. And this put selective pressure to increase the output of sound in order to enhance the sonar range and performance. This high output of sound eventually began to debilitate the prey against which it was directed. Eventually, through more natural selection, this stunning sound became so intense that the animal had to evolve structures in its head to protect itself from its own sound. Finally, the stunning sound was so effective that the teeth were no longer necessary and they began to disappear. This all sounds so logical, but does the fossil evidence support the theory? Dr. Larry Barnes is curator of vertebrate paleontology at Los Angeles County Natural History Museum.
We find the evidence from the skulls of both fossil and modern dolphins indicates that they have acquired through time the ability to produce ever more sophisticated sounds used for echolocation and other functions. When we look at a fossil dolphin skull such as this one, we find that it's symmetrical. The right and left sides of the face are the same. The midline is straight. However, when we look at this skull of a living pilot whale, we find the midline actually skews to the left side. This is an asymmetrical skull, and the bones on both sides are a different shape. Now, what this implies is that the bones actually have soft tissue sitting on them here. These are air sacs that sit on each side of the nostrils, the nostrils are different sizes and move to the left side. Now, these air sacs have been implicated in the production of sound, and the asymmetry is also implicated with the enhanced ability to produce very sophisticated sounds for echolocation. Now, these air sacs, as well as air sacs on the bottom of the skull, air sacs in holes such as these, surrounded by these bones, have actually been thought to protect the animal from its own sound. In the case of this modern dolphin skull, we see that there are actually bony crests that have developed, and these apparently act as baffles to actually channel the sound in a forward direction, right over the snout. The evidence from teeth is much less conclusive. In the case of this pilot whale lower jaw, we see there's actually reduced numbers of teeth. However, in other dolphins, like this one, we see increased numbers of teeth. In summary, there is evidence that toothed whales through time have developed methods to produce more and more sophisticated sounds. I can accept the hypothesis that some modern toothed whales do indeed debilitate their prey with such sounds.
This is the prototype. It's a sperm whale skull. The first of the toothed whales to develop the features of an advanced acoustical system. Protective bones, the asymmetrical skull, and the parabolic shape to reflect the sound. And it has withstood the ultimate test, the test of time. The sperm whale has remained essentially in this form for at least 23 million years.
If brain size is a measure of intelligence, the sperm whale is very bright indeed. Its brain weighs more than 8 kilos, the largest of any known creature, past or present. And significantly, it is the acoustical cortex of the sperm whale's brain that accounts for much of its size. A few crude weights and measurements are about all we know of the sperm whale, despite killing more than 1 million of them in 1.5 centuries of whaling. Our interest has been profit, not knowledge.
When whaling stations like this were still in operation, this was the object of the single-minded drive of whalers to capture every possible sperm whale. It's spermaceti oil. There's up to 1,900 liters of it stored in a huge reservoir in a sperm whale's head. It's highly prized by industry for unique biochemical properties not found in other oil. But it also has unique acoustical properties not suspected by whalers. Spermaceti oil is a superb transmitter of sound at twice the speed of a dolphin's melon. And it may very well be this property that explains how sperm whales are able to capture their elusive prey.
The spermaceti oil is contained in a case of dense muscle, which is in turn surrounded by a complex network of passages, sacs, and valves where air is recycled. It's believed that sound is produced by forcing air through an aperture called the monkey's muzzle at the front of the spermaceti organ, possibly under such intense pressure that a tiny sonic boom is created. When sperm whale clicks are played back at a slow speed, it's apparent they are not a single sound, but actually a series of sounds that scientists call burst pulses. On the sound graph, they show as an initial pulse, followed by a rapidly diminishing series of sounds, all within a few thousandths of a second. Ken Norris believed that analysis of these burst pulses held the key to understanding how sound is produced in the sperm whale's head. He theorized that the spermaceti organ acts as an echo chamber, reflecting sound between air sacs at the front and back and projecting it into the water. To test the theory, Norris had to have a click recording from a sperm whale of known length. He could then estimate the length of the whale's spermaceti organ and calculate how much time should be required for sound to travel down the organ and bounce back. If that time matched the pulse interval of the recording, it would support the theory of the spermaceti organ as an acoustical chamber.
One day down in Chile, we got our chance. My crew was out offshore in a Chilean vessel called a felucca, about 30 feet long, and they began to hear sperm whale sounds in the water. And the sounds kept coming closer and closer to the ship. And as you could tell, they got louder and the sounds began to speed up. And finally, believe it or not, they came right up under the vessel, and the sperm whale actually hit the underwater microphone or the hydrophone. And it then came up alongside the ship and rolled over. And the crew could see that it was just about the same length as the vessel.
Back in his lab, Norris timed the sound pulses and found that they matched almost perfectly with the length of the whale's spermaceti organ. This appeared to confirm Norris's theory that the spermaceti organ is a living echo chamber. But Norris's theory remains unproved because we've never had a sperm whale under our control where it could be studied. Only once, very briefly, has there ever been a sperm whale in captivity. In 1981, a young sperm whale was found stranded on a beach near New York City. It was sick and very weak, so the Coast Guard towed the whale to a boat basin where it could be treated. The whale was named Feisty, and 50,000 people came to see it. Richard Ellis, an author and artist specializing in marine mammals, got into the water with the whale.
It was making these popping noises, and I wanted to figure out what part of the animal the sounds came from. We didn't know whether they came from its mouth or its blowhole or somewhere around the nose, so I put my hand on the end of its nose, and the sounds it made were so powerful that even underwater, it actually lifted my hand off the nose. The sounds that it made popped my hand off its nose. I tried to keep my hand on the end of its nose, and as it made those popping noises, it lifted my hand right off.
We know so little about the sperm whale that even Richard Ellis's simple observation added significantly to our knowledge. After 10 days, Feisty recovered under treatment with antibiotics. He returned to the open sea and to a life that is still almost entirely a mystery to us.
Some scientists who believe that whales can use sound to stun think they acquired this ability near the end of a long process of evolution. If this is the case, we should be able to find it in the toothed whales that have the most highly evolved acoustical capacities. If this is true, killer whales are likely candidates because their vocalizations are so sophisticated. They actually speak, if we can use that term, in dialects.
Dr. John Ford has recorded and analyzed the calls of many of the killer whales on the British Columbia coast. He has discovered that they make up to 70 different calls. Some of these sounds are used by all the killer whales on the coast. Others are used by only a few. And there are sounds that belong exclusively to a single pod of whales. For more than a decade, Graham Ellis has been photographing killer whales on the BC coast. His photos are the key to an ingenious system for identifying individual whales.
This is an animal that has had a marking for many years that you can see runs across the saddle patch. And at the top of the fin up in here, there's a small...
At the Nanaimo Biological Station of the Canada Fisheries Department, Dr. Mike Bigg has compiled a killer whale mugshot file that enables him to identify just about every adult killer whale on the coast.
On this, and you can see that these markings are all identical. So this is definitely K-pod that you've taken pictures from.
Mike Bigg's whale catalog led to a fascinating discovery. It revealed that killer whales on the BC coast live in 3 completely separate groups that never mix, even when they come into contact. There is a northern population of about 135 whales, a southern group of perhaps 80 whales, and a transient community of about 50 whales whose exact range isn't known. Each of these groups is divided into a number of pods. From time to time, various pods will join together, but only temporarily, because each pod retains its separate identity, apparently for life. By painstaking analysis of his recordings of killer whales from all over the coast, John Ford has found that each pod has its own distinct dialect.
When you compare the sounds of different groups, you can see that in a certain area, some pods will share many sounds. These sounds often differ in very minor details, such as this particular call here, given by 2 closely related pods. At least they're closely related in that they spend a good deal of time together. Now, if we look at other pods that also occur in the area, we find groups that may produce entirely different calls than this other group. I think until we have a much better idea of what the actual sounds mean to the animals, how they use them in their day-to-day lives, we really won't be able to interpret these dialects in a meaningful way.
Killer whale dialects may preserve the identity of pods, or they could have a genetic purpose, controlling breeding patterns. We just don't know. But there does seem to be an explanation for the amount of vocalization. The transient pods are nearly silent, and this probably has something to do with their feeding habits. The transients prey on seals and sea lions like these. These animals have excellent hearing and would quickly take refuge ashore if forewarned by calls from killer whales. The feeding habits of the other whales are quite different. Fish, and especially salmon, are their favorite prey, and they are sometimes extremely vocal when they are feeding. Each summer, killer whales gather here in Johnstone Strait, behind Vancouver Island, to intercept migrating salmon. Some years ago, Don White was cruising beside a killer whale in the strait when a salmon surfaced beside his boat.
And he or she ran along the surface of the water for a little ways and then dove down, I would estimate 2, perhaps 3 feet, and all of a sudden stopped dead in the water. Made no move to get out of the way. It was almost like an animal freezing. The whale, without breaking stride, changing motion or rhythm whatsoever, just came up, and it was so easily opened her mouth, took the fish, and then kept on going. And it was as if something had stopped the fish. And the salmon, I mean, can get out of the way quite easily from an animal which is that size.
I've been able to watch killer whales chasing and catching salmon at ranges close to the boat on a number of occasions. In my experience, the animals use vision mainly. They really are usually silent when they're approaching the fish at close range. Perhaps they emit a few sporadic echolocation clicks, but no big bursts of sound. So if killer whales do have the ability to stun fish, they don't demonstrate it, at least when they're catching salmon.
Perhaps killer whales are more likely to use stunning sounds on small fish, like these herring. These sounds of killer whales feeding on herring were recorded off the coast of Norway. The loud crash is precisely in the most critical hearing range of the fish.
We've been trying in this program to determine whether toothed whales use stunning sounds. By now you'll appreciate the plight of scientists who are trying to answer this same question. They're learning a lot of interesting things about whales, but they really don't have a definitive answer. However, if we look elsewhere in nature, sounds do appear to be used to stun prey. Right here off the coast of California, in kelp beds, for instance.
Divers in inshore waters along the California coast often hear a crackling noise, like static on a radio. It's the sound of millions of animals like these. They are called pistol shrimps because of the sound they make with one oversized claw. Although they're scarcely 5 centimeters long, pistol shrimps can produce a noise so loud it can be recorded up to 1 kilometer away. The sound appears to be made by the closing of the claw, but it's not. Its true source is much more ingenious. The claw is held open by the tensile cohesion of a film of water between 2 smooth discs, hidden from view inside the hinge. The snap is produced by the force of suction when the 2 discs are pulled sharply apart, allowing the claw to close. In an aquarium like this, the snapping is a sign of aggression, as the shrimps compete for limited space to dig their burrows. The sound is also used to stun the shrimp's prey, in this case, a small but agile fish called a goby. To stun the fish, the shrimp gets as close as it can and then snaps several times. It's not a knockout, but the fish is slowed down enough for the shrimp to catch it. The struggle is violent but brief. A few rapid snaps close to the fish, and it's quickly subdued. Kathy Krieger is a dolphin trainer at the University of California's Marine Laboratory in Santa Cruz. She has just begun training 2 bottlenose dolphins in these new tanks that were specially designed to encourage dolphins to make loud sounds. For Ken Norris, it's a chance to determine once and for all whether toothed whales stun with sound.
What we hope to do here is to provide the capstone on this story. That is to train a dolphin to emit the sounds and then to watch what happens to a fish when it's hit by them. And if in fact the fish is killed, then we'll have our proof. And beyond that, I'd like to know what it means in dolphin societies to have every individual carry around a weapon, so to speak, a Saturday night special, that could actually kill other members of the school. What does that mean to the way their societies are built? Does it have anything to do with the cooperative nature of those societies?
Whales and dolphins capture our imaginations, not only because of their size and obvious intelligence, but because they're at home in a world that's almost a complete mystery to us.
They roam the seas over 4/5 of the planet's surface, often in the blackest depths, where sound is the key to survival. The proposal that toothed whales use stunning sounds may ultimately prove to be wrong. But right now, when we know so little, it provides a radically different way of looking at whales. And often, that's the way new insights are obtained. As we probe the mysteries of the whale's soundscape and their complex acoustical apparatus, it's exciting to realize how much we have yet to learn.